Hi everybody, Corey Shipe here, GIS 595. First homework, and this is a paper review for UAS for repeat landslide characterization. So the photo here in the bottom, just to set this up, this is a hill slope, and we'll get into the details of where we're working, but this is a hill slope that has failed in two separate events. You can see this kind of landslide 1 on the right, landslide 2 on the left. These occurred on this hill slope following intense rainfall events. This is pretty typical of what we get in the study area here in this example, but it's also typical of what we get here in North Carolina, in Western North Carolina in particular, which is where I am and working on this stuff. So the paper is Multi-Temporal UAV Surveys for Landslide Mapping and Characterization by Rossi et al. This was published in 2018. Full citation is here at the bottom. So we're working in Italy in this example, kind of getting near Florence, Italy. And what we're doing is, in effect, just imaging hill slope failures at 3 discrete intervals. There's 3 discrete times. These are some months apart from each other. Very simplistically, they're using an RGB camera on a drone, utilizing structure from motion for developing these digital terrain models, or DTMs, and then comparing those DTMs for subsequent characterization, trying to understand how these hill slopes are failing following or how they're changing following landslide events. The equipment on this, some images here on the right, this drone that they're utilizing is called the Saturn. Okay, the Saturn II. This is a homegrown drone by the folks there at the Department of Earth Science at the University of Florence. They utilize a circular frame, which is kind of unique. I don't know that I've necessarily seen this. There's 6 props on the machine, and the idea is that that circular frame allows them not only to modify the payload distribution a little bit easier perhaps on a quadcopter, but they can also turn on and off some of these props, just kind of balancing that payload versus the objectives of the mission and the flight time that they're after, etc. So if they just want to run 3 props, or if they want to run 4 or 5 or all 6, that's all in the cards. And they claim that they can even make this change during flight, which I find pretty interesting. So this unit, obviously GPS enabled, has fully autonomous capability. They can pre-program a flight path, set this thing up, let it do its mission, and it'll come on back to the home base there. The published runtime on this is 30 minutes. Here's the bare weight and max payload, up to 10 kg on the max payload. They've tested this up to close to 30 kilometers an hour, and so this is a constantly evolving platform. These folks are continuing to push the envelope. They're trying to make better and better drones. So this is always changing. Interestingly, the camera was actually a pretty simple Sony optical RGB 8 megapixel consumer grade camera. The funny part is, here in 2019, I can't even find this thing on Amazon anymore. I don't know that they make it, but it's a pretty simple camera. And so they had this mounted on a gimbal. It's what was utilized to capture the RGB imagery. So what's the application or the mission here? The ultimate objective, again, is just to repeat survey this hill slope that has failed. And we can just jump right into the image here at the bottom. This shows the 3 discrete sampling periods, the 3 times here in 2015, again in March of 2016, and then only a month later in April of 2016, they imaged this same hill slope. And in effect, the steps here to collect that RGB imagery, develop the DTM using structure from motion, repeat this at some later date, and then you now have multiple digital terrain models to compare, and you can look at volumetric change, you can look at a long profile change, etc. So you can see in these photos, okay, at time step number 1 or 0 perhaps, you have this headscarp forming. Okay, so this is looking up in these images. This is downhill, okay, downhill going up in the image. And so they have this existing kind of headscarp, maybe potential small scale slide that is occurring. After some rainfall event in early 2016, they had this relatively large scale here on the order of maybe 40 by 60 meters or so landslide develop and extend down slope. And then within the same, within about a month from that time, they had a secondary failure occur on the right side of the image. Okay, so and this is a typo here in the article. This should be LS2 for landslide 2, but that's here on the right hand side of the image. Okay, so now that they've done their RGB imagery, they've used structure from motion to get the digital terrain models, and now it's a simple subtraction problem, and they can understand how these surfaces are changing. So these plots here are both using that first survey prior to the landslide activity as a master, if you will, and the second survey on the left and the third survey on the right here being used to understand the change. All right, so looking at the difference between the first and the second survey, which if you recall was when that main landslide occurred, LS1, you can see the detachment area, which is shown here in orange. And what that is effectively areas where the elevation decreased. Okay, you lost material, that material traveled downslope. And then areas in blue at the toe of the slope here represent where the elevation increased. Okay, so in this case you had all this material in the red and orange detached from the hill slope, it flowed downhill, and it deposited here in this blue area. On the right hand side you see a very similar pattern. This is the first versus the third survey. You have a very similar pattern with LS1, but now remember we have this new landslide that occurred, LS2. And within there are two discrete slides, but it's a similar pattern. You have some red and orange area where you had material detach, it flowed downhill, and it deposited, in this case, about somewhere here mid-slope. But the same thing happened. You lost material here where it's this pretty big yellow area, and it deposited downhill of that. So at first order, their results are fantastic. I mean, this is great. They can use very simple camera technology and understand how hill slopes are changing following landslide events. So why do I care? And to illustrate that, let me give you an example. This is something that we're working on as part of the North Carolina Geological Survey's Landslide Hazards Program. This is an area near Saluda, North Carolina, where obviously this road is closed. I mean, this is we are talking 10 to 15 meters of displacement in some areas of this slide. This is a road that was running. It had cars driving on it as of December of 2018. We had a very, very wet 2018, and following a particular 5-inch rainfall event around the end of the year, around the new year here, coming into 2019, we started to get some pretty big failures. They've only accelerated pretty much following rainfall events. We can go out to this slope and we can continue to watch things moving down and to the right, downhill. So this is a prime example of where potentially we could utilize the technology from Rossi et al. To work on a local problem and try to understand how this is changing with rainfall, which is really a key component to mitigating further damage. There are homes in this example. There are homes down and to the right here. Obviously, this road being closed is impacting quite a few folks that travel this road every day. So there's a lot of reasons that we want to understand what's going on, and now potentially we can just use a pretty simple camera and some advanced analytics and get an idea. So that's what I've got. I appreciate your attention and look forward to the class.